my life. I'm so stressed out. I don't understand.
Okay.
That's a 5-star. That's so.
Okay, so we're starting with the multiple choice, or not the multiple, well, I guess these are multiple choice. So to begin with number 1, we want to know when to reject the null hypothesis. And it's really nice that I wrote this up here. You reject if the p-value is less than or equal to,
Is this number 1 in the
yeah,
first box, or-
less than or equal to alpha.
Do you have an extra study guide?
This is the last one I have. That's the last one. Okay, and if I just go ahead and rearrange that, we know that the p-value is 0.04. So in other words, we're going to reject if 0.04 is less than alpha.
And alpha equals 0.0.
No, alpha isn't given. The p-value is given.
Yeah, the p-value.
Yeah. So any alpha that's greater than or equal to 0.04 will lead to rejection. So we can think of some examples. Greater than or equal to 0.04, yeah. Some examples. Okay, I'm really getting tired of this. Include alpha equals, so I need anything bigger than 0.04. 0.10, sure. That would lead to rejection because 0.10 is greater than 0.04. Yeah, the one that you're likely going to see is 0.05. That would lead to rejection.
Anything higher than 0.04.
Any number that's greater than 0.04
So
will.
the answer is just anything higher than 0.04.
Okay.
Reject the null hypothesis?
We'll reject the null hypothesis, yeah.
Doesn't to reject to be less?
The p-value is less than alpha, yeah. If our p-value is 0.04,
Oh.
that means anytime we get alpha greater than or equal to 0.04, we're going to get a rejection. Okay? 2. Significance test allows you to reject the hypothesis H0 in favor of the alternative at a 5% level. Can we reject H0 at the 10% level? So what do we know about that p-value?
0.1.
We don't know what it is exactly. But we do know that it has to be less than 0.05. Since we are rejecting at the 5% level.
So alpha is the percentage of zero? Like for this one, it's 0.05.
Yeah. It's that level of significance level is what they call it. So, do we reject at the 10% level? at the 10% level? Yes. Since the p-value must be less than 0.10. It's already less than 0.05, so it has to be less than 0.10. Do we reject at the 1% level?
No.
Maybe. Since we don't know,
It has to be greater than.
yeah, the exact value, it may be of course it might not be less than 1%. We really don't know. All we can tell you is that alpha is definitely less than 5%. How much less? No idea. Questions on 2? Yeah.
Wait, so like is alpha like both 0.1 or and 0.05?
I don't understand what you're saying. What are you saying?
So like isn't alpha supposed to be 0.05?
Not necessarily. 0.5 is one of the customary levels of alpha, but you can set the alpha level depending on how comfortable you are with a type 1 error. It doesn't have to be 5%.
But like you 1% if you any
Yeah. You good?
So the p-value is the z-score.
No. P-value is the area.
Is the area between the z-score.
It's the area between of the tail between the z-score
Curve?
and infinity. Yeah.
Is it always going to be 5%?
No.
Will it be stated?
It will be stated. Yeah.
Okay.
Here the idea is, can we pinpoint exactly what the p-value is?
No.
No, we can't.
It's an estimation.
Yeah. All we can tell you is that the p-value is definitely less than 5%.
In any case.
No, in this case. In this case, it's less than 5% because they're telling you that you're rejecting at the 5% level.
Okay.
So since we're rejecting at the 5% level, we know the p-value has to be less than 5%.
So therefore, H0 can reject at 10% because it's higher than 5%,
Mhm.
right? And at 1%, it might reject.
Yeah.
Okay, yeah. And then HA, what does that stand for again?
Alternative.
So each alternative,
Mm-hmm.
is that just how you say it?
Yeah.
The hypothesis.
So Mr. Ray, this is like the FIQ that was like the values. Like it was like technically it was like 10, which fell in between. So the answer was actually like maybe it could.
Yeah.
Be. So this is like one of those.
Kind of like that, yeah. We just don't know what the actual value is. But we can't categorically reject. All right, number 3. We have a test, mu equals 100 against mu not equal to 100. Sample size is 80. We have a test statistic of z equals 0.8. What is that p-value? Okay, and then I think for this one, what is this?
I really don't understand. So then someone said
Okay, so for this one, what are we saying? We're saying that the test statistic is 0.8. And they told you it's a z-score, right? So this has a z-score of 0. And this, of course, is mu x bar. And then they're telling us we have a z-score of 0.8, which would be kind of like right here. And that would come from x bar. So the p-value should be the area in that tail. So this is the p-value right here. Both of these two tails added together.
Why both of them?
The null hypothesis is not equal to.
No hypothesis what? Because you have.
Not equal to.
Why?
This is what it says.
So the null hypothesis would be everything included except for the z-score.
No, then. Sorry. Let me start over again when I finish drawing this. Okay. So what we're saying is that the alternative. I said null hypothesis. That meant alternative hypothesis. The alternative hypothesis would be mu is not equal to 100. Okay. Since the alternative hypothesis is mu is not equal to 100, that means we have to use a two-tail test. So the p-value is going to be equal to 2 times the probability or the proportion of each tail. So this is the p-value, both of these together. Those are both the p-values.
And that's just with that formula. This adding it together.
Mm-hmm. So we have to compute that with a calculator now.
Quick question before we do that. How do you know if it's a one-tail test? Is there ever one of them?
Everything, it's only a two-tail test if the alternative hypothesis is a not equal to.
Okay, but if it's
Everything
greater
else
than
is
equal to, and then
one-tail test.
What do you look for?
How do you do that?
Okay. Second, vars. Normal CDF, which is number 2.
Nice.
Our z-score is 0.8, right? 0.8 to infinity. Let's paste that. And we're going to multiply that by 2. Because it's a two-tailed test. That gives me a p-value of 0.4237. Let's screenshot that.
Yes, zeros. Yeah, and then you multiply by 2, because you make it.
Is equal to 0.4237.
And that's how we should round it to.
If they're asking you by the
Always
p-value,
four.
you do know it's this.
P-value always 4.
So whenever they're asking you to do a p-value, you do the CDF.
Well, or TCDF.
Okay, how do you do the TC?
Hmm?
But how do you do the TC?
We'll be doing a TCDF later for sure. Okay. Remember, I don't know what I just did. That's not the correct one. Okay, so remember. HA mu is less than or HA mu is greater than a number are one-tail tests. Whoa.
How did you even get that?
Jenny.
Chinese traditional.
You should post everything online in Chinese just to see what it's used. They don't think so.
No, they just wouldn't study for that.
What's that?
So in this case, it is the number.
For this one, we did two purposes because it's like mu x is not on the problem itself.
Okay.
X is not equal to 3, so you don't take the
No, she's not. Oh my god.
Yeah, it's like bigger than or less than. So we just yeah.
This friendly
Hmm?
I really like overall.
program that like had like that tails question.
The which one?
Where you put the program on a calculator that had like one tail, two tail question.
That's either T inverse T or inverse norm.
So you do everything the same.
And if we use inverse norm,
You should rarely use that one for the inference test. Okay, and I think that's number 3, unless there are any more questions. All right, let's go 4. What critical value T star that satisfies the condition that the T distribution with 8 degrees of freedom has a probability of 0.1 to the right? Okay. So what are we saying? We're saying the area to the right is 0.1.
Oh, I missed a
Mhm.
So whenever you're given a z-score, do you develop that curve?
It's a good plan. Okay, that has a z-score of 0.
Is it always going to say the z-score?
Not always. This time it's a t-score. Or you don't, hold on. You have to find the t-score this time. Okay, so the probability is the same as the area. I'll get to it 1 second. And we don't know where it is. I'm just kind of estimating where this is. But we're saying the area here is 0.1. Which means, of course, the area over here, 0.9. And what do we need to know? We need to know the t-score up here. What is this? to go from area to t or z-score, use the inverse. Okay. So this is for a confidence interval, right? And they were telling us t for sure, right? So program inverse t. This is for a inference.
So this chapter is different.
This chapter is inference. And we're finding the area in one tail, right? It's my alpha level.
0.1.
0.1. Oh, 8 degrees. What's the 8 degrees of freedom for?
We'll get there in 1 second. Yeah, the area is 0.1. No, I'm sorry, the air. Yeah, 0.1. See, now it's going to ask for degree of freedom, and it's 8.
Wait, why is it 8?
Because it says with 8 degrees of freedom.
Oh, then
Let's screenshot that right now.
If you press enter, it keeps selecting.
It does?
The degree of freedom is 8.
Mm-hmm.
Oh, okay. That makes sense. Okay, point.
There we go.
You just want it for
1.397.
So that would be the T star.
That would be T star.
0.1, 'cause that's a- I don't know, there's just, and then the
Wait, is alpha your area? Is that what we're taking?
Yes. Alpha is the area.
And the DF.
DF is degree of freedom.
Oh, and then it says it.
Yes, it does. Tells you 8.
Yeah.
So that gives me my T star. T star is equal to 1.397.
Is that all it's asking for?
That's all it's asking for.
Okay, so to put it in the inverse T, infer the one tail, the area is 1.1, and the degree of freedom is 8. Is it always going to tell you the degree, like the degree of freedom? and stuff?
It has to tell you the degree of freedom if you're using a T.
Okay.
An alternative way of telling you the degree of freedom is to tell you the sample size as well.
Okay. And so if they were to tell you the sample size, how would you?
Remember, the degree of freedom is equal to sample size minus 1. So much, right?
Or
1 second.
equals to n minus 1, right?
Mhm. Thanks for waiting. What was it?
So you said that to go from area to T or Z score, use the inverse norm or the INVT programs. So is when you say inverse norm, is that just the way to calculate the Z score, not the T score?
The inverse norm will give you a Z-score.
Yeah, so you can't find the T score.
You can't find a T with that, yeah. You can get close, but you can't get the actual T.
What exactly is a T star? Like, is it just the like?
What makes this a T star is that this is the test statistic where we start rejecting null hypotheses.
Okay.
Okay. So in this case, if I got a T star that's greater than 3.97, let's say I got 1.62,
Okay.
then I would reject the null hypothesis.
Because it has to be what, greater than 1 or greater than 5, right?
In this case, it was 10%.
Oh, because it's 0.10.
Yeah.
Okay.
For two-tail hypothesis, when you're putting in your T or Z value in the calculator, is that value going to always be in the lower bound and you're going to put infinity in the upper bound?
For a two-tailed test,
Yeah.
yeah, always make it. I would always take that the test statistic, make it positive, and just compute an upper tail.
So put that in the lower bound.
Positive.
Positive.
Okay, anything else on 4? Okay, 5. Let's see if we get to actually do something this time. Five. We wish to test if a new feed increases the mean weight gain compared to the old feed. At the conclusion of the experiment, it was found that the new feed gave an average of 10 kilogram bigger gain than the old feed. A t-test with a proper one-sided alternative was done, and the resulting p-value was 0.082. Interpret this p-value. So that's basically, what does that sentence say?
Find the p-value.
Find the p-value.
Right, I mean, what does our summary say? If the null hypothesis was true, the probability of obtaining our sample is, what did we get for the p-value?
0.08.
Yeah, 8.2%. Yeah, 8.2%. Now, we don't get an alpha level, so we can't really make a decision here. So that's pretty much it. So we can interpret that a little bit more. If the new feed had the same weight gain as the old feed, sorry, more context.
Wait, is the new feed and the old feed had the hypothesis name?
Yeah, they're part of the hypothesis. Yeah.
Oh, that's correct. Is this kind of like contradictory? Like, if the new feed had the same average weight gain as the old feed,
Mm-hmm.
and the probability of obtaining a new feed that gains 10 more. Oh, so you pretty much think you cannot contradict. I'm confused. 8.2%.
Okay, so when we remember we're talking about like samples, there's sampling variability. So the sample that we get may not always have the same average as the population, because we could pick some pigs. I think we're talking about pigs here. We could pick some pigs or livestock that gain more weight and some livestock that gain less weight. And we're not sure exactly which ones are going to be in our sample. So because of that sampling variability, this 10 kilogram more weight gain should happen about 8.2% of the time because of sampling variability.
And since there's no alpha value, we just assume that it would be 5%.
Yeah, I don't think we just need to interpret the p-value. We don't actually have to make a decision.
Like if this was like a problem though, if they didn't get p-value,
Yeah, you would have used 5%. Oh yeah?
Who's the null hypothesis of this, that the new feed is gonna have the same average weight gain as the old feed?
Exactly.
That's the null.
That would be the null
And the
hypothesis.
alternative would be what?
The new feed has a more weight gain than the old feed.
So the p-value for both of those are the same.
No, we only compute the p-value once. Okay, and it's only for the null hypothesis. You don't do anything with the alternative hypothesis.
you always try to prove that this is wrong.
You judge based on the old, if the old hypothesis was correct, how likely would the probability of our sample be?
So our sample in this case is, the average of 10 kilograms more than.
Uh-huh. Yeah.
That's not the alternative.
No.
What's the alternative?
In this case, the alternative hypothesis is likely going to be the new feed has a greater average weight gain than the old feed.
It's greater than so we're proving that it's greater than
Okay?
we're proving that it's small.
Can we go to 6? We wish, sorry, you're thinking of using a T procedure to test hypotheses about the mean of a population using a significance level of 0.05. You suspect that the distribution of the population is not normal and may be moderately skewed. Under what conditions is it safe to use a T procedure? Okay. And that kind of gets to that checking the 3 graphs, right? Okay. So they've told you a few things. They've told you that the population is moderately skewed, right? Well, if we took a large enough sample, then it would be okay to use a T distribution, okay, even with that moderate skew. So if the sample size is greater than 30, then T procedures should be safe under or because of the central limit theorem.
What do you mean should be safe?
We're just hypothesizing. We can't be sure 100%, but pretty much we're going to do it anyways. Just kind of that handy rule of thumb, as long as that sample size is greater than 30, you should be able to use T procedures regardless of what you see. Failing that, if the sample size is less than 30, then T procedures,
How do you know it's 30?
that's just a rule of thumb
It's only gonna be 30.
for the central limit theorem, yeah. T procedures should be safe
If it's normal.
as long as the sample does not contain outliers. I think that's what we're saying here, right?
What is the central limit theorem?
Central limit theorem says that if you're computing a sampling distribution for a mean, that sampling distribution approaches normality
At 30.
with larger sample sizes. And so the rule of thumb for that is, as long as the sample size is greater than 30, we're going to have a normal or a normal sampling distribution.
So you're doing the central limit theorem because it says it's moderately skewed
Yeah,
to try and find the normality within.
exactly. Normality of the sampling distribution.
Okay.
That's the key. We're looking for the sampling distribution.
Which has a level. What is the significance of it? What would the 0.05 be used for in that equation?
It's unnecessary.
It's
You
just a
actually don't need
number?
that. Yeah,
So all you need to know is it has to be greater than 30.
yeah.
And since
It's kind of there to throw you
0.05
off track, really.
Since 0.05 is less than 30.
Oh no, we're not testing that yet.
No?
No. Whenever we do a inference test like this, a hypothesis test, an alpha level must be stated or implied. Okay. Anything else with 6 you want to talk about?
It's just basically asking when you can use.
When you can use T procedures.
So it's if it's less than 30. Because
2 things, or actually 3 things. You can use T procedures if the population is normal, regardless of sample size. You can use T procedures if the sample is greater than 30, regardless of population shape.
Regardless of what?
Population shape. You can use a T distribution if the sample is less than 30, provided there are no outliers. And there are no contradictions to normality.
no outliers.
We should write that down. We use a T distribution
We use a T distribution if the sample is
If.
less than 30, and there's no outliers or no contradictions to the normality. If, like, contradiction to the normality, that would be like something wrong with T, or what would you consider a contradiction of the normality?
basically just the outliers.
Okay, so just if there's outliers.
Yeah.
Okay.
If the population
And the T procedure and a T distribution are the same.
and number 1, population is normal. Sample size is large, greater than 30. Or sample does not contradict normality.
So basically, you're thinking of getting so basically, the TEEDS procedure is you're testing if it's normal and the sample's greater or less than 30. So that's what the TEEDS distribution test.
The way you're phrasing that's a little bit weird.
Yeah, because I'm not really
Yeah. These are the conditions for using the T distribution,
Okay.
not when to use the T distribution.
Okay, so what exactly is a T distribution?
T distribution is a shape of a sampling distribution under certain circumstances. Hmm?
It's like this,
It looks like a normal distribution,
so just like a normal.
but like little flat. Okay, I think we should go on to 7. We can talk about that a little bit more. An inspector inspects, obviously, large truckloads of potatoes.
Sharon, that was not that funny.
That was hilarious. Go on.
I'm glad to amuse you. Inspects large truckloads of potatoes to determine the proportion of the shipment with major defects prior to using the potatoes to make potato chips. Yum. Unless there's clear evidence that the proportion is less than 10%, she will reject the shipment. Oh, the inspector is a sheesh. To reach that decision, she will test a hypothesis. P is equal to 0.1 and P is less than 0.1, using a large sample test for population proportion. She selects an SRS of 50 potatoes from the over 2,000 potatoes on the truck, and 2 of the potatoes in the sample are found to have major defects. What conditions for inference about proportion using the hypothesis test are violated? What did we violate? So this is kind of one of those things where they set you up to do the test, but you don't actually have to do the test. Question is, what conditions for the inference about a proportion are violated? So let's take a look at those conditions. Number 1. First of all, mu pi, mu p is equal to pi, which can be approximated with p. What's my p in this case? 2 out of 50? 2 out of 50. 0.4. 2.
Wait, why two out of 50?
Do you need us to select one?
I'm sorry, I'm so crazy.
Yeah, why is it
It's 10%, right?
Yeah, or yeah, D is 10%. That would be the proportion of the.
Yeah.
Using the sample.
I think it's funny too.
Stupidest thing's funny. I don't know why.
Remember, that's equal to 10% from H naught. So sorry, I messed that up for you.
Do you need a spread population?
You know what?
Population like what time?
You would, except for they're not really asking for the population characteristic, so you don't have to write it down. There's nothing wrong with 1, right? Number 2, sigma.
These are 3 things you always have to know.
Yep. Is equal to the square root of p times 1 minus p. These should be pi's.
Wait, so P doesn't, it's pi that equals what?
Divided by n.
Just all under the radical.
Yeah.
It's all under the radical, yeah.
And then would be 2000 or the 50 from the SRS.
50 sample size, so 50. That's going to be the square root of 0.1 times 0.9 divided by the sample size, which is 50. All right. 0.424. Last one. Hello. Okay. Okay, I'll send someone out there to pick up the pizza. Thank you. Pizza? Who wants to go grab it?
I'll get it.
Thank you.
Plus, yeah. Roy's gonna steal the pizza on the way.
There's no guarantee we'll come back with them.
She may or may not come back with pizza. Just saying.
Do you end up getting a free one?
Huh?
Do you end up getting a free pizza?
No, I didn't use the free pizza
Why'd
How'd you get
free
free
pizza?
because they order so much.
So much pizza.
Last one. The conditions. So, first one was n
Wait,
times.
Oh, I didn't put a square root, never mind.
N times pi is equal to 50 times 0.1, which equals 5. Ooh. Which is less than 10. Bold. This is a
I don't
problem.
think we've ever actually gotten a less than 10.
There's always a first fiddle.
This is a problem.
Like we did something wrong, or that's just a trick.
No, well, they're asking you, where is the problem?
Oh.
What conditions are violated?
Normality? Is that the answer?
Yeah.
Cool.
N times 1 minus pi is equal to 50 times 0.9, which equals 45. 45 is, of course, greater than 5. This is not a problem.
Good than 10.
Bigger than 10, yeah. What am I doing? Thinking about pizza. That's no problem. So the only problem here is n times pi is not greater than 10. We cannot use a normal procedures because n times pi is greater than, no, is not greater than 10. And that's what they're asking for. You cannot use normal procedures because n pi is not big enough.
Thank you.
In other words, the sample is not big enough.
Because that's only possible.
So is that also like the 5%? What is that? What was 5% of the population?
Yeah, that's only for means. That's to qualify the standard deviation for a mean.
Has to be less than 5%.
Has to be less than 5% of the population, yeah.
Roy's face.
Right. Okay, so we're gonna take a small pause here for pizza. I'm gonna leave it recording, so.
Do you want receipts?
Oh, yeah. Let me get some paper towels. No, he's over here. There was some over there. There's some more? I'll get you some.
The caption for this is "You are trash."
That's all.
I like it.
Anybody want this butter?
I'll go.
Is there anything left?
There's one piece left.
What's Parmesan?
Adam, you want Parmesan? Tell you.
Oh, sorry.
Is that Parmesan too?
What was EY?
No, that's not pepper.
Sharon, you just ate. Sharon, look at what we've been doing.
Look who's talking.
Sure. Take us.
Yeah. There's obviously gonna be an altitude that says cost only for every ASB activity.
Well, does it usually get like, why can I come to this? Do you really like care? You're not gonna
No, just getting it clear.
Who's not going to bar?
What are you doing?
Getting pizza.
That's exactly what I asked her for. What are you doing?
What are you doing?
Gosh, Sharon.
Well, it first off in the wall, so that is in the digital phone.
That's nice.
No, you're not.
Well, Bar got to get excused for taking a stupid driver license. I think the excuse was also like.
They're a lot more understanding. But apparently my absences for my college sports games. I have to find my ticket. What?
Well,
Okay, now that I got to my sports book party, I never got to this. So you guys not there.
where do you want to go?
Wow. Nope.
Comes out.
Is tomorrow an early day?
No.
Today's Tuesday, don't
Wait, one second. Sharon was amazing.
Sharon, calm down.
Wait, what?
Cause she didn't know.
Do you want garlic sauce?
Babies.
Does anybody want garlic sauce? Alright, I've got another one.
Do you actually make money off of pizza?
No. I lose money every time.
You do?
Hmm?
I didn't like it.
I lose money every time. pizza.
Yeah, because it's not.
CSF like does.
$1 a slice is enough.
Big Mama and Papa's, they give like a better deal, I think.
Yeah.
No? Or which one do we use?
Amici, but you have to ask for Michael and you have to say that you're missing.
You have to say that you're missing.
All right, Sharon. No, because I mean, this pizza has a lot of cheese in it, so and it's very thick. So I would expect it to be at least $10 a pizza. And there's like 8 slices of it, so you're losing money. Plus it's delicious,
Hmm.
right?
That's right.
But I'm basically just eating pure fat right now.
Enjoy that, so it's okay.
I wore my running shoes.
Nice Yale shirt.
What?
Nice
Thanks, I'm going to Yale.
Really?
I got my accepted.
For sure.
Yeah.
You got what?
Or
I
accepted
went to
to
Yale.
Yeah? I'm still working on that.
Yeah, they were like, you're just too good at, we have to accept you. Yeah, they're like, you don't even have to finish this application, we want you. Well, it's because I know 4 different languages. What? I know. I hope you got to go, yeah.
He's not gonna go.
My friend Casey is going into,
UCLA, we're good. We're top 25.
Oh, no, thank you.
We're top 25. We have the right like SAT score. We're all good, right?
Look at the we already.
I don't think this is a we share. I have a great SAT score. I'm top 25. I'm a great
No,
person.
but like we.
I don't have a grade.
Did you take the SAT or ACT?
I'm so good.
Wait,
I got
what's
a
that
20.
equivalent?
What's all the 1600 now?
It's 16.
It's like
What'd you get?
1280.
Where'd you go? Where'd you go to college?
UCLA.
UCLA?
No.
No, because I know he went for his master's to one. I wasn't sure which one he went.
CSUN was
Master's.
master's.
Oh, you went to CSUN?
Are you gonna get a PhD?
Master.
Do you one day want to get a PhD?
No. I don't have a reason to go in.
It's more work.
I was considering applying to Princeton, and then I looked online. They're like every student before they graduate has to write a 360-page like thesis,
What?
and I'm like, yeah.
On what?
Not in
They
one
make a
sitting.
thesis on pizza.
Still.
Because they didn't say what you have to do.
360-page thesis to graduate Princeton.
So it has to be for like some of their BSs or something like that. Like can't be possible for every single major.
For
How come for
undergraduate.
number 7, the third part, we don't just say that n is greater than 30, so it's not?
No, because we're talking about proportions.
Okay, so for proportions we can't do that.
Mhm.
But if we were doing like sigma x bar and mu x bar, then we could do that.
Then we could do that, yeah.
I
Good
still
point.
have time to run to the restroom.
Yeah.
Is it open? Where is the bathroom open?
Yeah, this one is not toilet. I don't know if they put it in.
Take your toilet paper.
Yeah, take your
This school,
Yeah, I'm tapped up.
I don't know if it's true, but I think
They're
BYOTP.
bringing.
But
They're
it's
bringing
probably
more toilets.
Or who was telling us? Someone was telling us
Someone
like
said
the
it-
budget they spend on like just like toilet paper and paper towels is like 40,000.
Yeah,
I heard
it's,
something
like,
crazy like that, yeah.
ridiculous. Like that. I
And
came
yet,
up at
I
SSC
don't,
and
we
I was
don't
like,
see
wow.
any of it.
I
Do
know.
they like stockpile it
No,
every year?
because they have it, but the janitors
They just
put
don't
them
have
in.
anyone to restock the bathrooms. Like they're just not restocking them. They're just locking them. It's like, oh, this one's empty. I'm just gonna lock it.
It's just so annoying because like.
But I mean, like I feel like from
they're
sophomore
drunk.
year, like when we left over summer, Mr. Kodama's trash cans were still on when he came back.
We're still,
We're still
Wow.
where he left. And I mean, like if they say they don't have janitors to clean the room, then they're saying they don't have janitors to clean the bathroom. And they're saying they don't have janitors to clean up lunch. Where are they cleaning?
they don't have enough people to do it, really. It's like 4 people are supposed to clean the whole school overnight. I don't know. How long does it take to clean a classroom?
A classroom. I would say like, I don't know, like
I'd say like
15 minutes?
With 4 classrooms an hour.
of people, 60 classrooms now.
It's just so annoying.
Well, this has to be done every day, but I mean, like, they don't like step in your like.
They don't even come like once a month. They really don't.
It depends what you like clean.
Like mop the floors.
Okay, if it's like mop and floor, it's
So like they don't like I've been here where it's late. They don't even step inside the classroom. They
By
only
sophomore year, they
come out.
cleaned up after homecoming too. This year we have to do it.
No, they always cleaned up. The sophomore year they didn't know what
No.
was going on.
We're gonna do FRQ1 in class tomorrow.
okay. And then we did one of them today too, right?
Yeah, we did 2 of them today.
Oh.
So we only have 5 problems left. 8 through 12.
Yeah.
Yep.
Oh, awesome. I think we'll be done with.
I didn't even start them yet.
No, like, is it finally? Like actually.
No practice.
I know I am, but I really shouldn't. You know what I had today? You saw I had 2 donuts. I just had pizza.
Why do you have 2 donuts?
A donut and a half.
And so that was crazy.
Such a good boyfriend.
No, it's because they went home with me now.
Too nice. It's a donut and a half in advance. Not every It's less than because of the donut.
Why are you so happy?
So then,
Why is that so happy?
I did so fast. I'm really
why the
sorry.
faculty restroom really nice and warm?
No.
No, they're even worse actually.
The C building bathrooms are so nice.
Mr. Tucker just comes into the student restroom. He's pissed off to visit one of the teachers in line and just like comes in and he's like, hello, Chip.
You gotta go, you gotta go, I guess.
Did you watch the SNL 40th anniversary?
I did.
It was so fun. The celebrity
I
judges.
was watching.
Let it snow.
Four ads.
For us.
I don't know what.
It's not like what
Just celebrity
I caught Let It Snow. I didn't see Who Reads the first time, but I saw Let It Snow. So I was like, oh, I see it. There it is.
Did you see Adam Sandler's Up on That?
I didn't watch the whole
Yeah.
thing.
Yeah.
Adam Sandler comes out and he's like, SNL. Billy Ray's here, so we're over here.
Ew, did you see when Bradley Cooper made out with Betty White?
Yeah, that was
That was nasty.
Californication.
All right, let's get going with number 8.
He's actually my favorite SNL kid. He's the new like really young like black kid. You know who
Is Obama?
Yeah.
Okay, we have a random sample of 900 individuals. We're getting started.
he's like a kid.
It's found that 180 are regular users of vitamins. Thus, the proportion of regular users of vitamins is estimated to be 0.2. Standard error of this estimate. So we're looking for standard error. Okay, remember standard error is number 2 right here. That's my standard error.
The standard deviation thing.
Is the standard deviation of the sampling distribution. So in this case, it's sigma p. And that's equal to the square root of pi times 1 minus pi divided by sample size. Here we're estimating p with 0.2
P or with pi?
pi, yes.
And why is it 0.2?
They're telling us.
Oh, sorry. They'll always tell us that, right?
Yeah.
Either they'll have to tell you. Usually we would take it from step 1 here, but they're telling us to estimate it from here. Okay, 0.2 times 0.8 divided by sample size. What's my sample size? 900?
I think so, right?
One,
Yeah. 0.013.
Wait, does your
3.
do that for you?
Yeah.
Why don't we use like 180 instead of 900?
180?
Well,
yeah, it says 180.
there's like 180 people that use vitamins.
Because that's how many people use the vitamins. We're talking about the whole sample.
Thing.
whole sample.
180 is the 0.2.
It's like you're taking a survey of 900 people and only 180 have what you need, but you're still taking a survey of 900 people.
Okay. That was easy. 9.
That's done?
Yeah, that's it. 9. We have a null hypothesis that is actually false is rejected, is not rejected. Which one is this one?
Take 2.
See, null we failed to reject, right? We failed to reject. So that's a type 2 error, right?
Type 2, which means standard error? What is a type 2 error?
There are 2 types of errors.
Okay,
Type
is
1
the
and type 2.
HO and-
Type 1 error is when you reject the null hypothesis that was actually true. Type 2 error is when you fail to reject the null hypothesis that was actually false. Definitions. Type 1?
So it just wants us to identify what type it was?
Yep.
This is the type.
Type 2, yeah.
Reject a true null hypothesis. Type 2 error. Fail to reject a false null hypothesis. So that just goes by like definitions. Okay. A major tire manufacturer claims that his shock absorbers last for 5,000 miles. A consumer watchdog group claims that the actual mileage is lower. If mu represents the true average life of shock absorbers, what are the appropriate null and alternative hypotheses? Null hypothesis. Maybe we should look at the alternative hypothesis first. Alternative hypothesis. What are we trying to show? We're trying to show that the average is less than 5,000 miles.
Wait, I thought you said 500.
Okay. And if that's my alternative hypothesis, then my null hypothesis has to be the same value of mu but equal.
But equal?
Mu is equal to 5,000. The null hypothesis is always equal. These two numbers, 5,000 and 5,000, are always going to be the same.
And then HA is gonna be less than or greater than.
Yeah. 11.
Wait, then what about, in the previous, like, in number 3, it was not equal, unequal? Like, it was, a hypothesis alternative equals mu is not equal to 100. So when is it not equal? Like, does that just depend on the question?
Yeah, that depends on the question being asked. Suppose that we take a random sample of 5 from a normal distribution with an unknown mean mu and an unknown variance sigma squared. The null hypothesis mu equals 65 is tested against H alternative mu is greater than 65 at an alpha level of 5%.
H alternative is always less than.
It could be less than, it could be greater than, it could be not equal to. The resulting sample mean is 68.25. S squared is equal to 9. What is the value of the appropriate test statistic, the rejection region, and the conclusion? Wow, okay, so let's do all of those. First of all, the test statistic. You know, before we can do test statistic, we're going to have to do 1 and 2. So 1, mu x bar.
What's the difference between regular mu and mu x bar?
Regular mu is the average of the entire population. Mu x bar is the average
Of the sample?
of the sampling distribution. Mu x bar, that's approximately equal to mu. No, it's exactly equal to mu. And that's equal to, that's from our null hypothesis. Our null hypothesis is 65. Two. Sigma x bar. That's equal to sigma divided by the square root of n.
Because this is mean not proportion.
Wait, how is this different than from the other one? It was pi.
Because we're using mu instead of pi. We're testing a mu now.
And why are we testing? Just because the question, I think?
It's mean not proportion. The question's mean not
So
proportion.
it's asking for
Sorry, which is approximately equal to s over square root n.
what's x? The sample?
S is the standard deviation of the sample. Variance of the sample is 9, so the standard deviation is 3. 3 out of the square root of the sample size. What's our sample size? Yeah.
This is one more.
Thank you. Okay, so I think we're good to go here. We can't really do 3, but no, we can. Sample comes from a normal distribution. Use of normal procedures. Sorry, we're doing T procedures here, right? Should be safe.
Wait, why should they be safe?
Because it's normal.
There's what?
It says it's not normal.
Because, yeah, the population is normal. Test statistic T is equal to x bar minus mu x bar divided by sigma x bar. Which is equal to, what was my x bar? 68.25 minus mu x bar, which is 65, divided by sigma x bar, which is 1.342.
There's so many boxes.
2.42. That takes care of the first part of the question. Um, yeah.
If this was a z-score problem, the formula itself is the same.
Yeah. Let's get a p-value is equal to the probability that t is less than. Less than? Greater than. What am I saying? T is greater than 2.42.
Is it greater than because it says that the alternative is mu is greater than?
Wait, it's greater than because what?
The alternative hypothesis is mu is greater than 65. So because the alternative hypothesis is greater than, we're going to use a greater than sign here. Okay, let's get to the calculator and use our TCDF. Oops. Let me start over again.
Whoa, what do you have to TC?
TCDF.
Oh,
Shoot. Let's start over again. TCDF. Second vars. TCDF is number 6. A lower is 2 point. Is it 2.42?
Yeah.
2.42. Our upper is 1 E99.
Yes, what?
Our degree of freedom is 4.
How do you know that it's
Because
Sample size is 5.
so it's one less? It's always one.
Great. 0.364.
And we only do TCDF when we're trying to find the t-value.
P-value, yes.
Sorry, p-value.
Yes.
then if this was Z score, you would just use inverse norm.
You would norm CDF.
Oh yeah, that's
So the p-value is 0.0364. So we should reject the null hypothesis.
The rejection region would be the 0.0364.
We're not there yet, since p-value is less than alpha, which would be 0.0364 is less than 0.05. Let's get to that rejection region. Let's get this normal curve again. It only took me 4 years to figure out that I could do this
You used to draw it?
every time.
Oh yeah. I was with you.
You were with me.
Last semester.
Okay, let's label this all. Starting with here, the mean. That has a t-score of 0, and that was at 65. What's our t-score? 2.42. You okay?
Yeah.
T equals 2.42, and that was at 68.5, 68.25. And that's our p-value right there. To get the rejection region, we want to know where is the area of 5%. So we're going to have to do our inverse norm. So finding the rejection region. Okay, so no, let's go back here. We're going to norm, T, inverse T, using our program. We're doing this for inference 2. We have one tail. Our alpha is 0.05. And we have a degree of freedom of 4. Thank you.
So there's one.
So our t-stat was 2.132. Let's screenshot that. .132.
That's for rejection region.
That's where our rejection region begins. So what we're seeing at 2.132, which would be right about here. 2.132. T equals 2.132. All of this is my rejection region. That's my rejection region. So this is kind of a nice way of seeing that the test statistic from my sample is 2.42. 2.42 is bigger than 2.132. Therefore, we rejected. The rejection region is everything here where t is greater than 2.132.
Wait. Can you just say that again?
Yeah. The area above 2.132 is 5%.
Oh, okay. And
Okay.
then 2.42. The thing between 2.132 and 2.42.
Doesn't really matter. What's important is that 2.42 is bigger than 2.132.
Which is 5%.
So we would reject the null hypothesis. It's another way of deciding whether to reject that does not rely on p-values.
For the problem, if it's what is the value of the rejection region,
Mm-hmm.
we would put the t value, or we would.
Yeah, rejection. I'll write that down right now. So the rejection region is all t greater than 2.132. RT was bigger than 2.132, so we reject.
Equal to as well.
It could be equal, yeah. Since our t is greater than 2.132, we are in the rejection region, which is another reason or another confirmation of rejection. Again, it's another way of doing this without computing a p-value. since 2.42 is greater than 2.132, we can reject the null hypothesis. Last one, 12. They're giving us everything here to kind of figure out. Actually, 12 is pretty much just like 11. 12. Let's go through the 1, 2, and 3s. Number 1, mu x bar. That's equal to 58.2. 2, sigma x bar equals, do we have a sigma? Nope. So it's approximately equal to S over the square root of n, which is equal to 4.8 divided by, 4. 1.2. We don't really have to do part 3. So T is going to be equal to x bar 56.85
Use 58.2 for the x bar.
divided by sigma x bar (56.85) minus 58.2 divided by 1.2. Two-tailed test. The p-value is going to be equal to the probability that t is greater than 1.13. Sorry, 2 times.
Is it less than equal to negative?
Because it's two-tailed test, we're just going to take the positive tail and calculate the positive tail. You could do the negative tail, no problem. Okay, let's do this.
Can you go back to
Sure, no problem. I know I'm going a little bit fast here.
Where did the negative sign go?
Because it's a two-tailed test, I'm going to calculate the upper tail instead of the lower tail. Since the curve is symmetric, it doesn't matter which one we can do.
Wait, how did you find the tail?
I haven't done it yet.
Oh. Okay.
We're finding area though. So we can say it's going to be equal to, let's clear that out, 2 times TCDF.
Wait, why CDF aren't we doing university?
Nope. We're finding area.
Second VARS TCDF.
1.13. How many degrees of freedom?
How did you get 1.13? What is that?
1.13 was right here.
That's okay. That's negative. Why is it?
Right. We're changing it to positive because you have two-tail test. Two-tail test. Two-tail test. Okay, 15. Let's paste that. Calculate that. Yeah, that's not a lot. Or that's too much. What am I saying?
The degree of freedom is 15.
Degree of freedom is 15, yeah. What did I say? 2762?
2762.
Let's paste that on there.
So what do you mean by appropriate test statistic?
Hmm?
What do you mean by find the value of the appropriate test statistic?
Yeah, that would mean either T or Z. Which one is appropriate?
Okay.
Will we always use TCDF, or is there going to be a case where we use TPDF?
One more time.
Isn't there like 2 different T's? There's TPDF and TCDF.
You're never going to use TPDF.
It's always going to be TCDF. And then there's the normal CDF and normal PDF.
You're never going to use normal PDF.
It's always normal CDF.
Okay, and that's my p-value. The last thing that we're going to do here is the rejection region, right?
Yeah.
So let's get that graph and let's try and figure this out. You know, Sharon, I'm so glad I figured out how to do this.
Can you have these worst graphs? No offense. We
It's
were
okay.
always-
I know they're bad. Yep, have a good day. Okay, our rejection region, that's 5% in both tails. Note, two-tailed test. Two-tailed test. Therefore, the tails add up to alpha. Since alpha equals 0.05, each tail must have an area of 0.025. Okay. Let's figure it out. We're gonna.
So let me just get that from both
Yeah.
ones.
So if it was just a one-tail test, then one tail would be alpha.
Sorry, wrong one. We go here. We're going to use that program again. Inverse norm, or inverse t. Inverse, or inference. Oh, nice. Two tails. Alpha is 0.05. How many degrees of freedom? 15? 15? I forgot that I programmed it that way. 2.131.
So that would be the rejection region.
Yep. 2.131.
Which is greater than 0.025. Wait, would you divide that by 2 or would you just leave it?
Nope. 2.131. Oops.
Oh.
Oops. 2.131. So let's see. This would be my 0 right here, right?
Middle.
Right in the middle. T is equal to 0. And that's going to be at 58.2. And here at 2.131 is going to be our rejection. Maybe I should do that in red. 2.131. And then negative 2.131. This is our rejection region. Any t-value, test statistic that ends up in the rejection region will end up being rejected. What was our t anyways? 1.13?
1 point, yeah.
Yeah, 1.13, which is not in our rejection region, right?
Is 1.1.
1.13 is not in the rejection level, which is reason for us not to reject.
Since this is a two-tailed test, the 1.13 also be negative. 1.13.
Yeah. It's negative in the equation. It's initially negative.
Oh, you're right, it is negative.
Yeah.
Okay, let's get that. Negative 1.13?
Yeah. So that's bigger than the negative.
Negative 1.13. It's not in the rejection region, so we fail to reject. So we should write it down, our rejection region. That would be t is less than or equal to negative 2.131 and t is greater than or equal to 2.131. And again, since our t, our test statistic, is not in either of these regions, that's confirmation that we fail to reject. Okay? I'm sure we'll have more questions tomorrow. Okay, I'm gonna go email this up to you, and I'll see you all tomorrow. Thank you for staying around.